and welcome to Ground Source Heat Pumps Today and Tomorrow, hosted by Genius Energy Lab and me, Chris Davidson. Our agenda for today, we're going to take a look at Genius Energy Lab, and I'm going to tell you what we do as a company, and we're going to do that via a case study, which will talk you through a project that we've been working on. Then we're going to talk in a whiteboard session about ground source heat pump applications, including hybrid and heat network systems. Then I'm going to talk about myth busting, and there's plenty of myths to bust around ground source, so hopefully that will be useful for you. I'm then going to talk about the very exciting and interesting hybrid between solar and ground source heat pumps, and then deeper geothermal before talking about ground source heat pump as a long-term asset. Now, as we're recording this session today, my colleague Duncan is on, and he's going to be asking questions as we go through on your behalf. So who are we and what we do? We've well over 2 decades now of experience in ground source heat pump systems. A number of my colleagues were involved in a contracting business, but we started Genius Energy Lab about 7 years ago now. We've got well over 750 megawatts of systems installed as per our work. And what we're all about is giving the specialist input. I'm going to talk about our customers in just a second. That specialist input gives project substance, lowers risk, and makes sure we're all giving our customers the best possible advice. And a number of our customers here, as you can see, a lot of big consulting engineers use us for that specialist advice. We also work a lot with installers such as Kenza Contracting, for example, who we do the majority of their design work for. Also with our customers, so for example, a lot of end users like councils and universities and so on. So just as an example of a Justice Centre in London, which is just about to start construction now, we started with informal early engagement on the project, and it's really, is ground source feasible at that location? Does it make sense? Are we talking nonsense even thinking that ground source might work in that location? Now, we don't look to charge for that type of advice. So anytime you're looking for that early advice on a project, please do just get in touch. In this project, we then moved on to REBA Stage 2. We're following the REBA stages in this, just to hopefully dovetail with what you're thinking yourself. And in that instance, we did a feasibility study, including a desktop geological analysis and a preliminary ground loop design, which then spat out some system efficiency modelling, which helped with the energy statements for the project. Now, it's very important that the process we use for that preliminary ground loop design is exactly the same as what we would use for a detailed design towards the end. So all things being equal, we're not going to get any surprises down the line. We then moved on to REBA Stage 3, much more design assistance, again, more ground loop design, quite a bit of structural input on this project because the boreholes are actually going under the footprint of the building. We then developed project program, cost analysis, and then at the end of Stage 3, we specified some test bore packages, which were installed about 18 months ago now. In Stage 4, we got into more detailed design, so that's full system design specification, and actually at that point, we're more getting involved in design team meetings rather than issuing reports as we did at earlier stages. And then finally, well, we are either going to be novated over to the main contractor, or we're going to stay client side to provide oversight for the project. Some projects go one way, some go the other, but it just depends on what the structure of the packages actually are.
Worth adding that we work very flexibly and can support the process either way.
Absolutely, absolutely. So I'm going to drop out of PowerPoint now and into our whiteboard session, where I'm going to start by describing very briefly how a heat pump works. I'm then going to go into the design process we apply, and then I'm going to talk about some design specifics on different system architectures as we go through. So if we start with the heat pump here, so a heat pump, if I'm asked to describe a heat pump, I'll say it's simply a box that moves heat from a cold place to a hot place. So it just moves heat like that. How it actually does it is it manipulates the pressure in a liquid gas circuit to allow that gas to evaporate, and therefore, sorry, that liquid to evaporate, turn to a gas, and therefore pick up heat at a low temperature, and then condense, and therefore drop that heat at a higher temperature. It manipulates the pressure in that liquid gas circuit by using a compressor, which consumes electrical energy. And there's also another part down the bottom here, which is the thermal expansion valve. And that's simply a pinhole that keeps the high pressure on one side and the low pressure on the other. It's actually quite complex what goes on inside that TXV. So it's a good one to have a reading round if you're interested in a bit more detail. So enough said about heat pumps themselves. Let's talk about the design process that we go through for ground source heat pump systems. And ground source heat pumps are systems. They're not just a box. There are more components to it than just the heat pump itself. So let's look at a cooling system on the left-hand side here and a heating system on the right-hand side. And let's do some definitions, get some definitions on the board for you. So the heat being extracted from the ground is called the heat of extraction. And the heat being rejected into the building is called the heat of rejection. And there's a third part of energy involved, as I mentioned earlier on, which is the electrical energy consumed by the heat pump to make the thing work. Now, through the forces of friction, very, very close to 100% of that electrical energy ends up as heat also. So the heat coming from the ground is actually added to by the electrical energy being consumed by the heat pump. So our heat being rejected into the building is very, very close to equal the heat being extracted from the ground plus the electrical energy. In cooling mode, now things are reversed. So our heat being extracted is being extracted from the building, and our heat being rejected is into the ground. And again, we have our electrical consumption to consider. And again, through the forces of friction, that electrical energy is added to the heat that's being taken from the ground, and this time it's taken from the building, and this time it's being put into the ground. So whilst the processes of heating and cooling are similar, they're not identical because of the difference in where that electrical energy ends up as heat in the system. So the design process that we go through to design a ground loop, and I'm going to talk primarily about boreholes, closed loop boreholes at the start of this discussion. Towards the end, I'll talk about other types of ground loop as well. So go on, Duncan.
What are the typical heating efficiencies that you can expect, given that there's energy coming out of the ground?
So the range heating efficiencies that you normally expect would be sort of 3 to 4 units of heat being delivered into the building for every unit of electrical energy that's being consumed. You'll actually get slightly higher efficiencies than that in cooling, because the temperatures at which you're cooling are very close to the temperatures that we're encountering in the ground. But typically speaking, 3 to 4 units of heat being delivered for every unit of electrical energy. Now, if we've got a heating and cooling system, or there's some heat recovery going on in the system, which I'll talk about in a second, then those efficiencies can be significantly higher.
Thank you.
So based on the building load, so the heat we are putting into the building and the heat we are taking out of the building, we really need a breakdown of those loads to a minimum monthly breakdown, but we can't actually use hourly load profiles now and do our design. So based on what's going on in the building in terms of the heat being put into the building and the heat being taken out, and based on the properties of the heat pump, because the ratio of electrical energy to heat being extracted, heat being rejected is different depending on what refrigerant gas you're using, what compressor architecture you might be using, what types of heat exchangers, and so on. So given what's going on in the building and given the properties of the heat pump, how much pipe do we need to put in the ground to make this ground loop sustainable in the long term? And what I mean by sustainable in the long term, if we look at a heating only system for a start, then we year on year would expect that ground to get colder, but what we don't want is just getting colder and colder and colder. What we want it to do is tend to a limit within the efficient operation of the heat pump. If we're now looking at a heating and cooling system, then the graph will go in both directions. And again, we don't want it just getting hotter and hotter or colder and colder, but we want it to be working inside that efficient operation of the ground loop. So that's what we mean by a sustainable ground loop in the long term. The temperatures are manageable and within the capabilities of the heat pump.
With regards to long term, how long a term can these systems be designed and operated for?
Well, the standard design lives for them are 20 to 25 years, depending on which standard you're working to, but you can design them for as long a design life as you like. If we do design it for 20 or 25 years, it's not going to stop working after that time. And most of the time, most ground loops have reached their equilibrium point well within that anyway, so they're going to effectively work indefinitely. We are commonly doing design lives, however, of 100, 125 years for that Justice Centre I mentioned in London earlier. That's got a 125-year design life on it.
Thank you.
Okay. So let's look at how we apply this to, let's start with a commercial building. So in this commercial building, we've got heating and cooling going on. So the cooling heat pump here is taking heat from the building and putting it into the ground. And we've got a couple of heat pumps here, then heating. So right away, you can see we've got energy recovery going on in that ground loop. Now, there's quite a number of systems that can do that energy recovery instantaneously, but the real magic of ground source is we can actually do that heat recovery interseasonally. So we can put heat into the ground in the summer and get that heat back out in the winter. Now, it isn't universally the case that we can do that, because let's, for example, say we've got an aquifer down here and we've got groundwater moving in that aquifer. It's just going to wash that heat away. So energy recovery in that instance might be very close to zero. Whereas if we were in a high density, low permeability rock, for example, then we could get above 90% energy recovery of that system. So let's now look at what happens. Let's say we are in the summer here. We've got these in the winter, sorry, we've got these two valves closed, these two valves open to allow those two heat pumps to deliver heating. Let's say we're moving into the summer now, and so we can close these valves off, open these valves up, reverse this heat pump, and we've now got two heat pumps cooling and one heat pump heating. And the selection of these heat pumps is really very important. We've not just got to understand what the peak loads are for the building, but how that load breaks down, what character that load has throughout the year. And one very common mistake that's often made in these systems is, let's say we've got a small, say 10 kilowatt server room load that's all year round. And let's say we're now in the winter, we've got all our heat pumps here, all heating. To deliver that 10 kilowatt load, we've maybe got a 100 kilowatt heat pump here. And we'd have to reverse that heat pump, turn it on, and it's like accelerating, decelerating, putting your car in forward, reverse. It's very bad for both efficiency and the reliability, the longevity of that product. So a very common solution to this, let's say just to dedicate a small 10 kilowatt heat pump connected into the ground loop that will be doing that 10 kilowatt server room load. So a very basic system. There are plenty of other architectures for closed loop ground source systems providing heating and cooling, but that's just a typical one as an example.
Going back to the interseasonal energy recovery, is it possible to tell from the desktop the suitability of the geology for interseasonal energy recovery, or is that found out at drilling stage?
Oh no, we can, the desktop analysis we can do because we've got excellent geological records in the UK and in many parts of the world, particularly in the UK because geology as a science was invented here. So the records go back an awful long way, so we can tell pretty accurately what's going on, both in terms of different layers of ground conditions and if there's groundwater, if that groundwater is likely to be moving and so on. So yeah, it can be almost all done on the desktop. Great question, thank you. Let's start looking at other applications now. So this is a multiple residential central heat pump system. So we've got some heat pumps down here in the basement. They are delivering heat up a highly insulated high temperature riser up to heat interface units in the dwellings. Now these heat interface units will be delivering, say, domestic hot water at, let's say, 65 degrees C, could be lower. And it could be doing space heating as low as 35 degrees C. But because we've only got one riser, we'll have to run at that higher temperature to deliver that domestic hot water. And the key thing about heat pumps is the bigger the temperature difference, the bigger the lift between the source down here in the ground and the load, the more electrical consumption it's going to make. So it's going to be less efficient. It's going to be less efficient. I liken that to say, let's climb a small hill. We're going to use less energy than if we're climbing a big mountain. So what we're doing is we are compromising that space heating efficiency because we're running everything at that 65 degrees C. Another important point to make about these systems is that there'll be a sale of heat agreement associated with each kilowatt hour of heat delivered into that dwelling. Now we can contrast that with a distributed heat pump system. So right away now you can see there's no central plant on this. There's not even any central pumping on this. The tiny little pump that's inside those little heat pumps is enough to drive enough fluid for that one heat pump around that loop on its own. And the benefit of this is we can now start to run at our domestic hot water temperatures at 65 degrees. We can then turn off that domestic hot water and run down at 35 degrees C for our space heating. We could also reverse that heat pump and provide cooling. So we could be providing, say, cooling at 6 degrees, 12 degrees return on that circuit. Or indeed, we can actually use that ground loop directly for cooling as well. So we're not now compromising our space heating efficiency in order to deliver our domestic hot water. One final point to make on this is that all of the run costs associated with that dwelling there are associated with the electrical consumption of the heat pump. So we've got quite a different technical and commercial solution between the two options here. Almost always when we do feasibility studies comparing these things back to back, because we are not now compromising that space heating efficiency, this one almost always comes out the more efficient solution. However, the sale of heat agreement here can be very important to the economics of that system. So we've got two different solutions. In terms of installation costs, they are remarkably similar. We did a feasibility study fairly recently where the system installation was going to be £4 million to do the project, and it was £4,000 difference between the two solutions. So they are very, very similar in terms of installation cost.
Is the solution on the right otherwise known as a fifth generation network?
It's a good question. So at the minute, the definition of fifth generation, I've even heard people talking about sixth generation heat networks now, is up for debate, and nobody's really defined or had a definition accepted universally. They're very often called ambient heat networks as well. So yeah, there's a lot of debate around that at the moment. There's quite a bit of hostility amongst the more conventional heat network people towards these ambient heat networks, which is why the definition of fifth generation is certainly up in the air at the moment.
Can you link different types and different generations of heat networks together?
Yes, indeed. Yeah, absolutely. And I can come back to that in a moment when I talk about connecting heat networks together. So thank you. Super. So let's talk a little bit about the hydraulics of these systems and how we design the hydraulics. So the hydraulics are there just to move the fluid around the closed loop. So for example, we've got 6 buildings here. It could be 6 dwellings. It could be 6 commercial buildings. Doesn't really matter. And if we've got a number of buildings connected to the same ground loop, then if you imagine you're designing a 4-way extension lead, electrical extension lead, you're not going to assume that you're going to have a 3-bar electric fire on all 4 sockets, or else your cable would be much bigger. It's a process called diversity. You assume that not everything's running flat out all the time. So we can take some diversity in terms of these ground loops and assume that not all of these buildings are going to be running flat out all the time. And that actually might save you a little bit of borehole. The downside, however, of connecting all these together is that these pipes, these header pipes, start to get very big. And so there is a balance between more connection of more buildings, more heat pumps, getting greater diversity, but then pushing your headers up. An alternative to that is to break a heat network like that up into pieces. So in this case, we've got maybe one borehole between 2 dwellings. And in that case, this collector pipe might actually be bigger diameter than the header pipes themselves. So we've got a balance between the two approaches. And in reality, of course, good engineering, you make compromises and you do a bit of both. So here we've got a little crescent here where we've got, this is Park Erin in Wales, Ken's a contracting project. It's been installed now for a couple of years. All the houses are now being occupied. And this little crescent here, we've got 5 boreholes here supplying these 10 houses here. So that's one district heat network there. Now, if we look at up here at array 28 and 29, array 29's got a couple of boreholes feeding those dwellings there, and array 28's got 4 boreholes. Now, they are not in hydraulic contact with each other. They're separate systems. However, they are close enough together to be in thermal contact with each other. So when we're designing a project like this, we can't just look at each individual array and design that. We've actually got to look at the overall project because of the thermal interference between the boreholes. Now, as you can see, we've got boreholes spread out all over this development. You can see we've got nothing in the roads, and that's because the roads were going to be adopted by the council. So we've kept all the boreholes in the gardens of the properties. And what we actually do is when we're designing these, we actually plot them on an imaginary XY axis. So each borehole has got its X and Y coordinates. So the software actually looks at the accurate locations of that boreholes relative to each other when it's doing the calculations as to how much pipe we need to put in the ground to make it sustainable, as I was saying earlier on.
How do you get effective balancing of these systems? Because in the real world, I doubt you can guarantee getting every borehole to exactly the same depth.
Yeah, so there's a thing called pressure drop in systems. So as you pump water around, one common misconception, if I go over here, is that we're actually lifting the water up the borehole. But what's actually happening, of course, what comes up the borehole goes back down. So that's gravity-wise a neutral process. So what we're doing in pumping is we're overcoming the frictional losses. It's called pressure drop in these systems. Now, if our boreholes are not the same depth, then because the longer the pipe, the higher the pressure drop, the longer boreholes are going to get less flow. So there are a number of different ways you can actually balance the flow. Commonly, you use manifolds, which have got adjusting valves on them. You can use restricted header locations. So perhaps a borehole that's further away will have bigger pipe to supply that header. One that's closer might have a smaller pipe to artificially increase the pressure drop. Rule of thumb is that you want no more than a 10% difference in flow rate between your individual boreholes. And there are, as I say, a number of different ways of achieving that.
Is the configuration in that diagram known as a reverse return?
Yes, it is, yeah. So a reverse return header, which is, you can see here, is a self-balancing header arrangement. So if you walk a path, if you like, down this nearest borehole here, and then back to the header again, and you walk at the same path through the farthest borehole here, then you can see that it's the same length of path. So that's the beauty of the reverse return header, is it's self-balancing. Downside of the reverse return header is, of course, you don't have any valving connecting each borehole. So if you were to, in a very unlikely event, lose a borehole, then you'd have to dig up that borehole header to isolate it or replace it.
That's interesting. How often do you lose boreholes?
Well, we counted up recently for our marketing purposes, and I think I've in my career in 20 odd years been responsible for something like 50,000 boreholes being installed in the UK and around the world. And to my knowledge, we've lost 3 of those boreholes, and they were all on one site. And it's because we think there's a coal mine underneath there that we knew was there, but we think that the coal mine has either collapsed and crushed some boreholes, or it's gone on fire and it's burned the pipe. So yeah, very unusual occurrence, but yeah, it does happen, but very, very rarely. And of course, on bigger systems, you've got the opportunity to build resilience in to for that to mitigate those kind of problems.
Thank you.
Increasingly now we're looking at mixed use networks. There's a thing coming up in the autumn, consultation coming up in the autumn, which will be looking at heat network zoning, which looks like it will allow local authorities to declare a heat network zone and then have some form of compulsion to then connect to that heat network once it's built out. So for example, if you go up to a supermarket at the minute and say, we can connect to your cooling system for your refrigeration and connect into our heat network, they're probably going to see that as risk, hassle, something they don't need to worry about, so they won't connect. However, if you do get that compulsion, then to put that heat into the network and then take it out, utilising other types of building, is a very, very effective, excuse me, way of doing ground source and balancing that ground loop temperature out, improving the efficiency of the cooling and the efficiency of the heating. And the real magic, of course, is that interseasonal energy recovery I talked about earlier on. Sorry. Now, back to your question a second ago, Duncan, about heat networks and how they can be connected together. We can connect various ambient heat networks together, and because of the diversity and the differences in the loads between those networks, we are naturally going to get energy flowing to and from, which will make both networks more efficient. We could also connect this to an older generation heat network. One common problem in 3rd and 4th generation heat networks is the return temperatures coming back higher than they're designed to be. So we can take some of that heat and put it into our heat network. This could also be a data center. It could be a combined heat and power plant. It could be a waste to energy plant. Doesn't really matter. Any industrial process, we can recover that heat. And so connecting these things together is a very exciting way of looking at heating and cooling. Okay, so I've so far talked about closed loop boreholes. So what are they? Closed loop boreholes are very simple in construction. They tend to be about 150 millimeters in diameter across. They tend to be most commonly 100 to 300 meters deep. And most of the time they've got a single U-tube of polyethylene pipe installed in them, and then that's completed with a grout material. Now that grout material is there to do two things. One is to protect the ground so that no pollution, for example, could get down that borehole. So it seals off, provides a sanitary seal for the borehole, but also it provides thermal contact for energy to flow to and from that borehole. So that's the most common solution for commercial ground source systems. Yes. There are other alternatives.
On closed loop boreholes, I've often seen mainstream big named consultants using rules of thumb on watts per meter.
Yes.
What are your thoughts on that?
It's so variable that any rule of thumb you use is likely to be misleading and frankly useless. The range of output you can get depending on depth of borehole, depending on geology, and depending on nature of your loads, heating and cooling, for example, it could be as low as 3 kilowatts a borehole, could be as high as 30 kilowatts a borehole. So you see, applying a rule of thumb to this is very, very difficult, and you're almost certainly going to be wrong. Put it another way, I've given up guessing how much boreholes a ground loop's going to need because I'm always wrong. I just put it in the design software and get a definitive answer back off it. So there are alternatives, horizontal trenches, for example, more common in residential systems. In the UK, we tend to be about 1.5 metres deep, 1 metre wide, and I tend to prefer, rather than coils of pipe that you would have commonly seen slinkies in magazines, I like these straight pipes in the trenches. They're just a bit more forgiving if there's any variations in how the system works. So as I say, mainly for larger residential systems where we've got a bit of land available to us, and that can be installed relatively inexpensively. We have done them in schools and things like that where you've got playing fields perhaps as well. So that's the second type of closed loop system. So it's a closed loop of fluid, the same fluid circulating around that system all the time. We can then have a look at surface water systems. So anytime we've got some surface water, we can put some heat exchangers into that water, and we can take heat out or put heat back into that water. And as long as we are balancing the heat in and the heat out with natural gains and losses from that body of water, again, we've got that sustainable system. The main gains are solar gains, and the main losses are actually via evaporation. So these systems can be very, very powerful, and particularly when we start to look at new build multi-residential, new build business parks, things like that, to include an element of surface water for landscaping, for maybe sustainable drainage as well, and double the utilization of that by doing heating and cooling as well, can be incredibly attractive and can be a lot less expensive than boreholes, for example. So that's the closed loop of fluid circulating. So it's the same fluid circulating round and round. We do have the alternative of open loop. So this is when we're taking water from the environment, warming it up or cooling it down and putting it back into the environment. Now these open loop boreholes are much bigger. They're water wells. They can be up to a couple of meters in diameter, for example, 2 meters in diameter. And they've got quite significant construction. So they'll be maybe steel lined down into the ground. They might have packing material here to filter that water. We've got pumps down the bottom, and those pumps pump up through a heat exchanger, warm it up or cool it down, as I say, and back into the ground again. And then in time, it will migrate across here. So it is a loop, but there's that open element to it. Now, a couple of things to point out on these. You do want to make sure that you've got adequate spacing between your abstraction and your recharge wells to make sure you're not getting any short cycling on these systems. So we might be putting water into the ground as low as, say, 4 degrees C, and we don't want to see this water, which is perhaps starting at 12 degrees C, start to drop in temperature as a result of what we're doing at the recharge well. Second point to make is there are statutory licensing requirements in the UK for these types of systems. The regulations are different in England, Wales, Scotland and Northern Ireland, but in the main, any size of system is going to require statutory licensing, and that licensing process can take over a year. So that's a significant issue when you're talking about construction projects. And then finally, water quality. is variable. So in the chalk aquifer under London, which is very good quality water, you'd be looking at servicing these pumps and these heat exchangers on maybe a 12 to 14 year interval. Whereas some other aquifers up in the northeast, for example, or whether you're interfacing with coal mines, for example, water quality is a real problem. You could be having monthly maintenance in some cases there. So the rule of thumb generally that when I'm teaching this is that if you can do technically and economically do the closed loop alternative, then that's a safer bet. But it is an excellent technology, open loop, in the right application and with the proper geology and so on being done.
For closed loop applications, what licensing process is required?
There's currently none.
Is that for the water systems that you showed on the previous slide as well?
Yes, yeah, there are. The most of the time when you're doing a surface water system and that body of water is not necessarily owned by the customer, or it's perhaps in contact with surface water, such as a river, there'll be a planning application required, and bodies, for example, the Environment Agency, have the opportunity to then contribute to that planning application. So generally speaking, it's not required for closed loop systems, but for open loop, there will be permitting and licensing required.
I believe there is a planning application required if you're in a source protection zone 1 for closed loop.
Yeah, it's a good point. Okay, so let's look at a real system now. This was designed by myself about 15 years ago. It's been up and running for about 13 years now. It's a building called One New Change in London. If you imagine standing on the dome of St Paul's Cathedral looking east, it's at your feet there. And we've got 3 layers of shops and restaurants, then 3 levels of offices above, a rooftop bar and restaurant up there, which is a super place, particularly on a nice summer's day. The brief on this project was to do the maximum we could with the geology available to us. So in this instance, there was unusually big and deep piles on the building. So we utilised those piles to put loops inside the London clay. Now, the London clay is quite a low conductivity ground condition, but it's got a very good energy storage characteristics. So that becomes our interseasonal energy store. And we're actually actively managing the temperature in that interseasonal energy store. And we can do that in several ways. It's a bivalent system, so we can schedule cooling and heating loads on and off of the system to take heat out or put heat back into that ground loop. And we can also use our water wells here, which utilise the water that's in the cracks and the fissures in the top of the chalk to then temper that ground loop. And what we're actually doing is we're managing that ground loop between 20 to 25 degrees C most of the year. And the reason we've picked that point is if you draw a graph of these particular heat pumps in heating and cooling mode, the efficiency, that's where they cross over, is that 20 to 25 degrees point. Last time I saw some numbers on this system, we were achieving a seasonal coefficient of performance. So how much energy do we get delivered divided by the electrical consumption? And we were getting 6.8 in cooling and 4.8 in heating. So very, very high efficiency systems. Okay, so if you've got no more questions, Duncan, I'll drop back into the PowerPoint.
Lovely. Thank you very much, Chris.
Okay, so myths. There's plenty of myths around ground source, and we all have an obligation to bust them. So people talk about freezing the ground. We do run at negative temperatures in ground loops, but if you are seeing effects in a building structure or its surface as a result of that, then you've got an unsustainable ground loop. So you don't have enough pipe in the ground, in short. Lots of reasons why you can't do ground source, because you've got archaeology, for example. People think you can't do it in archaeology. Source protection zones, coal mines, hard rock, soft rock, all the reasons why you can't do ground source are all spurious. It's very unusual that we just cannot do ground source in a given location, but you'll very often see it written off in consultant engineers' reports because of poor use of rules of thumb, for example. That's a very common one. I saw a large business park system, multi-megawatt system, written off by a consultant because they couldn't fit enough horizontal trenches in. Well, you're never going to do a multi-megawatt system with horizontal trenches. It's going to be boreholes. So it's just, again, poor understanding of the rules of thumb. There's a real balance between reliability and complexity in these systems. There is unfortunately a tendency for people to overcomplicate ground source systems, and that has an adverse effect on reliability. And conversely, you can build in reliability to a system by keeping them nice and simple. So ground source can be more reliable than virtually any other heating and cooling solution out there because of it's buried in the ground and it's a very simple system. We get quite a lot of people coming to us selling miracle loops, as we call them. So it's a new ground loop geometry, it's a new construction of ground loop, whatever it's going to be, that's going to give you 6 times more than anything else. What I can absolutely categorically tell you is that if the ground won't give you the heat, you can't take it out sustainably. So it doesn't matter what you put in the ground, almost always the limiting factor is the conductivity of that ground itself. So just be a bit skeptical about people saying we can do a lot more than others. I've talked about coefficient of performance, so that's how much heat we get delivered into the building in heating mode divided by the electrical energy required to do it. And COP, coefficient of performance, is by definition at a single point. So for example, for air source heat pumps, it's 7 degrees on the source and 35 degrees on the load. For ground source systems, 0 on the source and 35 on the load is the standard rating point. So back to my point there, the temperature difference between source and load is inversely proportional to the electrical consumption. So electrical consumption goes up as we increase that temperature. It's not fair to compare a ground source standard rating point at 0 degrees 35 with the air source at 735. In order to do that properly, you need a seasonal coefficient of performance. So that's the annual heat delivered divided by the annual electrical consumption, so average throughout the year. Now in ground source, to come up with that seasonal COP is relatively straightforward, actually. The software will actually produce a seasonal COP as part of the design process. For air source, it's a bit more complicated because you've got to take account of not just the air temperature, but you've also got to take account of the humidity in that air as well, because when you're heating, you are cooling down the coils on the outside of the building. You'd naturally get then condensation from that wet air, and that condensation will freeze, which effectively would stop the heat pump working. So it needs to defrost. And so proper consideration of that defrost cycle is very, very important. We contributed to some work by Element Energy fairly recently, and we concluded that in the UK, real world UK, you should be looking at 2 to 2.2 for an air source seasonal COP and 3.5 to 4 for a ground source COP if it's designed and installed properly. Life cycle costs are hugely important when it comes to heat pump, looking at the various alternatives. Now, increasingly, for example, developers, they're building 2,500 houses. Most of the time, sorry to be cynical, developers are looking at building the cheapest boxes they can build. So they'll perhaps try and get away, now they can't do gas, they'll try and get away with direct electric heating, which would obviously be very expensive for the end user. And most of the time planners won't actually allow them to do that. So generally they're considering air source heat pumps. And that's because they think it's cheaper. But when you start to look at life cycle costs on the system, and I'll come back to that in a second, ground loops as an asset, then you start to really come in the favour of ground source. So if that initial cost or purchase cost is the only consideration, then probably air source is the best solution. But if you've got any view on life cycle cost, then ground source is going to be a significantly less expensive whole life cost of ownership.
Are there not other initial costs, though, that start to become a factor when you look at an entire project holistically, such as the electrical infrastructure?
Absolutely. So because air source heat pumps are going to be consuming more electricity, they need bigger electrical infrastructure to support them. There's a cost associated with putting that electrical infrastructure in. Other points to make on air source also is that they require roof space or high level space to then operate. So for example, there's a project in London we're looking at the moment where we took air source heat pumps out of level 10, which is the prime retail space in that building, and we moved that into the basement, and we got about £4 million extra revenue, annual revenue for that space that was then able to be let out. So there are other economics that come into it other than just initial cost and run cost savings as well. And I think that, you know, if you go to university and you learn about renewable in your building services engineering course, You'll very often be taught about simple payback, which is simply the installed cost divided by the annual run cost savings. And I think that's a really poor measure, actually, of the effectiveness and cost effectiveness of heat pump systems and renewable energy systems in general, because you've got to look at that whole picture. I mentioned space required. It's often exaggerated. And then one thing that I do quite a lot of is lobbying work on behalf of the Ground Source Heat Pump Association. And I get very frustrated when I talk to politicians and talk to civil servants. They think about the world on a house-by-house basis. So if you start to mass roll out ground source and do it on a house-by-house basis, it's going to be hugely expensive. Whereas if you start to look at it from a street-by-street point of view or a town-by-town point of view, then the economics come in much, much more strongly. Really interesting and exciting area at the moment is the hybrid of solar and ground source heat pumps. So let's just draw a very simple system here. We've got a heat pump there, which is fed off a borehole, and we've got a hybrid going on here. Let's say we put some solar photovoltaic on there. So that's absorbing solar radiation and generating electricity. So it's generating our electricity for us, and our heat pump utilizes that electricity. So it's a hybrid, but it's a kind of trivial hybrid. What you can then do is, instead of just going for solar PV, solar PV, we can go with solar PVT, photovoltaic thermals. It's got a backing on the PV panel of a solar thermal element. And via a heat exchanger, we can then connect that up to the ground loop, and we can put heat into that ground loop. Now that has a massive efficiency uplift on that heat pump system. So from that typical 3.5 to 4 seasonal COP, we've got a system running in Cardiff. It's been running for a couple of 3 years now, and that's up at 5.5 seasonal COP. So massive efficiencies. And because you're cooling that solar PV panel, you're increasing the electrical generation efficiency by something like 25%. So it's a win-win in all regards. Deeper geothermal is one of the big buzzes at the moment in the industry. So as I mentioned earlier on, we are normally drilling between 100 and 300 meters down for our normal systems. To get to electrical generation in the UK, you're talking 3 to 7 kilometers, those kind of depths to generate electrical energy. So what we're now interested in is this middle ground here, where we're getting higher temperatures than we are at those shallower depths. So we're getting more of a geothermal gradient, and we're also getting more per borehole. And the depths I'm talking about here, 800 meters to 3 kilometers, those kinds of depths where we're getting significant increases in temperature. So these systems are starting to be installed now, and it's a very interesting development in the marketplace.
Yes, what are the typical sizes of drill rigs required to drill the different depths of hole you've
different depths? So you're 100 to 300 meters. Yeah, you're talking about a tracked rig, which is maybe 4 or 5 meters long by a couple of meters wide, so it can be transported on a low loader on the road. To get to your very deep 3 to 7 kilometers, you're talking about, it's like a factory. Think an oil rig on land, it's that kind of size. And then in the middle, you've got these 800 to 3 kilometer deep. They are bigger rigs, more substantial bits of kit. So they might have a footprint of something like 10 meters by 6 meters, that kind of size. So it goes up the deeper you go. Okay, finally then, ground loops as an asset. This is, again, one of the big buzzwords in the industry at the moment. So when the gas pipe was installed in my house before I bought it, the owner at the time didn't pay for that gas pipe to be installed. They've effectively bought it over time by buying the gas. So what we're increasingly doing now is looking at ground loops in that same way. So these assets are going to be installed. They're going to be there for over 100 years. They can then be financed and sweated as an asset over the long term. So very much like the broadband networks, water pipes, gas pipes used to be, and electricity pipes, they are a long-term asset that are very attractive in terms of ownership for people like pension funds, for example, who understand these, understand the long-term ownership of assets. So any questions you've got for us, there's our email addresses there. Please do send through any questions you've got. And unless there's anything else from you, Duncan, we can call it a day at that.
Thank you ever so much for spending time with us today.
Yeah, thanks so much for your time. Have a great day.